So in MFT technique, we have seen that the memory is partitioned into a number of fixed partitions, where different partitions may be of same size or it may be of different size. Then the jobs are allocated to those partitions depending upon the requirement of the job. So if the amount of memory needed by a particular process is less than any of the available partition size, in that case the job can be allocated to that free partition. But the problem in case of MFT techniques that we have seen that it leads to two kinds of fragmentation. One, we have said that internal fragmentation. The internal fragmentation arises because of the fact that if a partition of larger size is allocated to a job whose size requirement is less than the partition size, and because the partitions are pre-decided and it is fixed, a partition cannot be allocated to more than one job at a time. Okay, so if I have a partition of say 100 kilobytes and the job requires say 50 kilobytes, and the 100 kilobytes partition is allocated to the 50 kilobytes job, in that case the remaining 50 kilobytes memory cannot be allocated to any other job, and that is an wastage of memory, which is referred to as internal fragmentation. And we refer external fragmentation. We have seen that there is another kind of fragmentation which is called external fragmentation, and external fragmentation is due to the fact that even if we have some partition which is available, which is free, but the size is less than the size requirement of any of the jobs. That means even if we have some free partition, we have jobs in the queue which are to be allocated the partitions. The partitions cannot be allocated to the job because the size of the partition is less than the requirement of the job. So the entire partition is an wastage, and we call this as an external fragmentation. In addition to these two, we have also seen that to protect every job against other jobs, we need two kinds of bound addresses. One we have said as lower bound register, or LBR, which contains the least address space of the particular job, and other bound that we have mentioned as upper bound register or upper bound address, which tells you that what is the maximum address that is to be referred by that job. Okay, so whenever any process generates a address for access of memory, the address is checked against lower bound register content and upper bound register content. If we find that the address generated by the process becomes less than the content of lower bound register, in that case there will be an interrupt which will terminate the job. Similarly, if the address generated is greater than the upper bound register content, then again there will be an interrupt following which the process will be terminated. So we expect that the address generated by the process will be within the lower bound address and upper bound address. And we have said that this concept can be extended to what we have said as base register and limit register. So base register is equivalent to the lower bound register. Okay. So whenever the process generates any address, the address will be generated in the logical domain. The address is generated in the form of logical address, which is to be added to the base register content to give you the physical address within the memory, the location which will be accessed. Okay. And whenever the logical address is generated, we have to check whether the logical address exceeds the limit register content or not. If the logical address exceeds the limit register content, then again we assume that the process is trying to access some partition which is not actually allocated to this particular process, so the process has to be terminated. Okay. Now we'll see that there is another kind of memory management which is called MVT, that is multi-programming with variable number of tasks. Unlike in the previous case, that is in case of MFT, where the number of partitions were fixed. So once you have fixed number of partitions, the maximum number of tasks which can be contained in the main memory is also fixed. And it is the number of tasks which are there in the main memory that decides what is the length of the ready queue. Okay, or the number of tasks which are ready for execution by the CPU simultaneously. So this is the number of tasks which are there in the main memory that decides what is the degree of multiprogramming. And in case of MFT, the degree of multiprogramming is fixed because the number of partitions are fixed. In case of MVT, we don't have any such pre-decided partition. Rather, the partitions are created of appropriate size when they are needed. So as such, there is no fixed partition. The number of partitions may vary depending upon the size requirements of different jobs and depending upon the number of jobs that you have to execute on the machine. Okay. So the number of because the number of jobs are variable, so the degree of multiprogramming is also variable. Okay. So that is what is exploited in case of MVT, which gives you multiprogramming with variable number of tasks. So let us see how this MVT works. As before, the memory is initially divided into two partitions. Let us put it like this. So I will always have two partitions, at least two partitions. One of the partitions will be allocated to the operating system, which is true whether it is MFT or MVT. In both the cases, one of the partitions have to be allocated to the monitor part of the operating system. Initially, when there is no job loaded in the main memory, I'll have a single user partition. So initially there are only two partitions, the partition given to the operating system, and I have a single user partition. Let us assume that our memory size is suppose 256K kilobyte. Okay, out of which say 40 kilobyte is given to the operating system. Okay, and suppose I have a number of jobs, so job J1 which requires 60 kilobytes of memory. I have job J2 which requires say 100 kilobytes of memory. Job J3 which requires say 30 kilobytes of memory. Job J4 that needs say 70 kilobytes of memory. Job J5 that needs 50 kilobytes of memory, and I have job J6 which may need say something like 60 kilobytes of memory. Okay. Let us also assume that the execution time for job J1 is 10 time units. For job J2 it is 5 time units. For job J3 it is 20 time units. For job J4 it may be say 8 time units. Job J5 it may be 15 time units. For job J6 it may be say something like 9 time units or whatever it is. Okay. And suppose the type of scheduling that we will use is the first come first serve type of schedule. That means the process which has arrived first will be loaded first in the main memory. Okay. So these are the number of jobs. This is the memory requirement, and this is the CPU burst. Okay. So now let us see that following MVT techniques, how these jobs will be allocated in the main memory. So we have assumed that I have 256 kilobytes of main memory. So this is address 0. Here I have 256K, out of which 40K is given to the operating system. Okay, now we come to the job queue. So when 40K is given to the operating system, I have remaining 216K as a single user space, as a single partition. Now, first I have in the job queue, job J1 whose size requirement is 60K, and I am assuming that I go for first come first serve type of scheduling. Okay. So job J1 has to be put into the main memory first. So whatever partition I have, that is of this 216K, I make one partition of size 60K, okay, and put job J1 in this partition. And here the boundary will be 40 plus 60, that is 100K. Okay. So after doing this, so you find that I had a single user partition which I have divided into two partitions. One partition of 60K is given to job J1, and the other partition of 156K, that is remaining as a free partition. The next job J2 whose size requirement is 100 kilobytes. Okay, I have free partition of 156 kilobytes. So obviously I can divide this into two partitions. One partition of 100 kilobytes which can be given to job J2, okay, and here the boundary is 100 plus 100, that is 200 kilobytes. Okay. After this, so right now I have four partitions in the memory. First partition is given to the operating system, the second partition given to job J1, third partition is given to job J2, and I have fourth partition of size 56K which is still free. Now come to this list again. In the list, the next job J3 whose size requirement is 30K. Okay. So again this 56K can be divided into two partitions. One partition of 30K can be given to job J3, so this boundary becomes 230K. Okay. And I have another partition, I have created another partition of 26K which is free. Coming to the list again, other jobs, we have job J4 whose size requirement is 70K. I have job J5 whose size requirement is 50K. Job J6, the size requirement is 60K. None of these jobs can be fitted into the free partition because here the free partition size is only 26K. Okay. So this 26K, at least at this moment, will remain as a free partition. This is the fragmentation, and this is an external fragmentation because this does not belong to any allocated partition. But you find that there is no internal fragmentation. The internal fragmentation is totally avoided. But in this case, we will have external fragmentation, right? But later on, we will see that in some cases, we prefer to have some internal fragmentation rather than totally trying to avoid it. Now, let us see what happens after 5 time units. Because this situation of the memory will be existing for 5 time units because job J2 after 5 time units will complete execution. So after 5 time units, job J2 will complete its execution one CPU burst, and the situation will be like this. The first partition of 40K is given to the operating system. Second partition is still with job J1. Third partition is now becoming free, and fourth partition is still with job J3. Okay, so this is 0, this boundary is 40K, this boundary is 100K, here it is 200K, here it is 230K, and this is 256K. So I have these three partitions, here a 56K free partition, and here I have a 100K free partition. Okay. Now coming to the job queue again, the next job which is there in the queue is job J4, whose size requirement is 70K. So what I do is, this 100K partition is again divided into two partitions. One partition of 70K is given to job J4. So this is 170K. And the remaining is 30K. And this 30K partition cannot be allocated to any other job, because job J5 needs 50K, job J6 needs 60K. Okay. So again, this 30K will remain as a free partition. Okay. Now, again, after 5 more time units, what will happen? The execution time of job J1 was 10 time units. So I assume that by this time 5 time units is already complete. After remaining 5 time units, job J1 will complete execution. Okay. So again, the situation will be different. I will have situation like this. Okay. So you find that here I have a new free partition of, so these are already existing free partitions of 30K and 26K, and here I have created a new free partition of 60K. Right? Now, the size requirement of job J5 is 50K. So what I can do is, again, this free partition can be divided into two partitions. One of 50K, which will be allocated to job J5, and this 10K, the remaining 10K, will be available as a free partition. Okay. Again, after some time, when sufficient memory is available, I can allocate job J6, but job J6 cannot be allocated at this moment. Right? Now, one more advantage with this MVT technique is that I can go for some replacement of jobs in this memory, what is called memory compaction. Because here you find that the size requirement of job J6 is 60 kilobyte. Okay. What is the total free space in the main memory? Here I have 10K, here I have 30K, so 40K plus 26K, that is 66K. So total free memory available is 66K. The requirement of job J6 is 60K. But in this situation, I cannot put job J6 in the main memory because I don't have 60K partition, 60K amount of memory contiguously available. Whereas if I go for memory compaction, that is, I'll try to put all the allocated partitions to one end and all the free partitions to another end, try to merge all those free partitions so that you get a larger free partition. Okay. So if I go for such compaction, then the situation will be something like this. First partition will go to OS. Second partition is occupied by job J5. This one is occupied by job J4. This one is occupied by job J3. And I'll have 66K partition at the bottom. This 66K now can be divided into two partitions. One of 60K can be given to job J6, and I'll have a remaining 6K partition which is free. Okay. So by using memory compaction, I can immediately allocate job J6 into the main memory. So this is an advantage that you get in case of MVT technique, which is not available in case of MFT technique. Okay. Now we have to find that what are the informations that I need to maintain to implement this MFT algorithm. As we have seen that in case of MFT, for every partition, we have to know that what is the starting address of the partition, what is the size of the partition, and what is the status of the partition, that is whether the partition is free or the partition is allocated. Here also, I have to know that what is the starting location of the partition, what is the size of the partition, and status of the partition. I'll say status when the partition is already allocated. In that case, the status field will contain not only allocated, but to which job it is allocated. So that is one table that I can maintain for all the partitions which are allocated. I can maintain another table which tells you what is, I won't call it a partition because the partition is not really decided for all these free areas. This may be broken into several partitions. So instead of calling these free areas as partitions, I will call them as free areas, and I will maintain a free area table. So I can maintain two tables. One is allocated partition table and the other one is free area table. In case of free area table, what I will put is what is the starting location of the free area and what is the size of the free area. Okay. Now I just said that in some cases we will allow some internal fragmentation. Ideally there is no internal fragmentation because always we have created the partition depending upon the size that is required. So there is ideally no internal fragmentation. But you find that when a partition size becomes very small, maybe 10 bytes, 15 bytes or 100 bytes, if I maintain that small partition as a free area, in that case for that I have to have an entry into the free area table, and it may so happen that the number of bytes that is needed to maintain that information is more than the size of the free area itself. Okay. Not only that, the size of the free area may be so small that no job can be fitted into that. Okay. So in such cases, it is better that instead of maintaining such a small amount of free area as a separate free area, you allocate that with one of the allocated partitions. So by that, you can avoid maintaining one entry in the free area table. Okay. So effectively what you are doing is you are allowing a small amount of internal fragmentation along with the external fragmentation. External fragmentation will naturally arise in case of MBT technique. Internal fragmentation ideally is not present, but we allow some internal fragmentation to avoid the costing problem. Okay. And to maintain this information, I think in our last lecture, last class on data structure and objective presentation, we have talked about some data structure where all this free area information can be maintained in the form of a linked list, where the linked list itself will be created by the free areas themselves. Okay. So there are two ways in which this information can be maintained. One is by maintaining the tables maybe in the OS area of the operating system, because that has to be in the system area, or this information can be maintained in the form of a doubly connected circular linked list, and the linked list can be formed by using these free areas themselves. I don't need any extra memory for making this linked list. Okay. So both these techniques, MFT and MVT, they are suitable for multi-programming applications or multi-user systems. However, one disadvantage that we have said is, see, just now we have seen that J6, which in this situation cannot be allocated in the main memory, though total amount of main memory is more than the size requirement of job J6. But this problem can be avoided by making use of compaction technique. But compaction is costly because the moment you start compacting, until and unless the compaction is over, the CPU cannot perform any fruitful task. Okay. So the compaction, though compaction is a possible solution, but it's a costly solution. So you should try to see whether there is any other alternative, so that whenever the memories are available, the sum of free memories, total free memory is larger than the requirement of a job, the job can be fitted, irrespective of whether that entire memory is available as a single partition or the entire memory is available as multiple partitions. Okay. So that is what gives rise to the concept of what is called paging technique. So we'll come to paging technique or paged memory management technique. Now, what is this paged memory management? In case of paged memory management, every process is divided into a number of pages. Okay. Similarly, the main memory is divided into partitions whose size is same as a page size. Okay. And the partitions in the main memory are called frames. So every job or every task is divided into number of pages, and the main memory is divided into number of frames, or the page size is same as frame size. Okay. Now, how do you break a task into a number of pages? So we can put it like this. So if I have, suppose this is the logical address space of a process. I say that this is logical address space. That means the starting address in this logical address space is always 0, and the maximum address is whatever is the length of the job. This is divided into a number of pages, where every page is of same size except the last one, which may be of size less than the page size, and that is quite obvious. Okay, and I have this main memory. The main memory is divided into number of frames where the frame size is same as page size. So this is main memory, and this is the logical address space of a job. Okay. The pages will be numbered as 0, 1, 2, 3, and so on. Frames will also be numbered as 0, 1, 2, 3, 4, 5, 6, 7, and so on. Okay. Now find that because I have divided the job into number of pages, I have divided the memory into number of frames, and the job page size is same as the frame size, it is always possible to fit any of these pages into any of the frames. Unlike in the previous case, where this entire logical space has to be fitted into the main memory in contiguous memory locations, now it is no more required. Obviously, some of the frames in the main memory will be given to the operating system. It may be one frame or more than one frames depending upon the size of the operating system and the relative size of the operating system with respect to pages. Okay, and the remaining frames can be allocated to user jobs. So it may so happen that the frame number 1 is allocated to page number 2 of the user process. Frame number 3 may be allocated to page number, say, 1 of the user process. This may be page number 0, this may be page number 3, something like this. I can place any page in any of the frames. Okay, but you find that when the process, when the CPU executes this process, the CPU will generate the logical addresses without bothering about where these pages are placed. So I must have some mapping which tells me that for a particular logical address which has been generated by the CPU, the page corresponding to that logical address in which of the frames it is loaded. Okay. So there must be a mapping function which maps the logical address space into frame number. Then once I know the frame number, from the frame number I should be able to find out the physical address. Okay. So for that, let us see that how Yeah, and whenever some address has to be generated, the logical address has to identify the page number in which the logical address corresponds and the offset within the page number to give you a particular location within the logical address space. Okay. So if I assume that every page will be of size say p number of bytes, this is the page size. Okay. And if the CPU generates a logical address say L, this is the logical address. Then as we said that this logical address has to be broken into two components. One is the page number, let us put it as lowercase p, and other one is offset within the page, let us say it is d. So every logical address has to be converted into a two component address or an ordered pair PD, where P gives you the page number and D gives you the offset within the page. So for example, if every page size here is say 10 bytes and the CPU generates the logical address of say 5, then that address 5 will be in page number 0 and the offset within the page number 0 will be 5 only. If CPU generates an address of 12, page size being 10, so logical address 12 corresponds to page number 1 and offset within page number 1 is 2. Okay. So I have to identify that what is the page number and what is the offset within the page. From the page number, using some mapping function, I have to identify the frame number where that page number 1 is loaded. And offset within the page will be same as offset within the corresponding frame because page size is same as frame size. Okay. So offset 2 within page number 1, because page number 1 is loaded in frame number 3, will be offset 2 within frame number 3. This is one-to-one mapping. Okay. So for every logical address, I have to convert the logical address into an ordered pair of the form page number and displacement within the page or offset within the page. How do you find it? It is very simple. P is nothing but L integer division capital P, where capital P is the page size. So this div indicates that it's an integer division. Okay. So earlier example, 5 div 10 will give you 0. 12 div 10 will give you 1. So this is integer division. And the offset within the page, that is D, is nothing but L mod of P. Okay. So just by using these two functions, I can find out the page number and I can find out the offset. Okay. Now how can we convert from page number to frame number? Because that is what is needed. Because once I know the frame number, the physical address within the main memory will be simply, say, physical address will be simply frame number minus 1. If f is the frame number for a generated page number, so that will be f minus 1 multiplied by page size plus offset, isn't it? This is the physical address within the main memory, the memory location which is to be accessed. Okay. So the paged memory management technique will be something like this. CPU generates an address, and I assume that this address is generated in the form of an ordered pair P, that is page number, and D, that is displacement within the page. Okay. Using this page number, I have to identify, I have to find out the frame number where this page is loaded. For that, I need some mapping. And what I use is what is called a page map table or PMT. So this is a page map table or PMT. This PMT will have a number of entries. Okay. Zeroth entry in this PMT or zeroth or first entry in this PMT will contain the frame number where page number 0 is loaded. Next entry will contain the frame number where page number 1 is loaded. The entry after that will contain the frame number where page number 2 is loaded, and so on. So if I use this page number as an index to this page map table PMT, the output of the corresponding entry in the PMT will be the frame number where the page is loaded. Okay. So this is the frame number F. I make use of this frame number. Along with this offset D, okay, the frame number comes from here. So the frame number along with this offset D gives you the physical address. This is the physical address within the memory location where the required data will be either written into or read from. Okay. So this is the main memory. And as I said, that the simple relation that you have to use is, once you know the frame number, it is frame number minus 1 into P, that is page size, plus the offset within the page. That will give you this physical address where the data will be accessed or the data will be written. Okay. So using this simple technique, now you find that if the size of a job is 100 kilobytes, I don't need that 100 kilobytes of main memory should be available contiguously to load that job. Okay. Whereas if the page size that I use is the 10 kilobytes, then what I need is 10 number of frames, free frames, wherever it is available. It may be available contiguously, it may not be available contiguously. But my requirement is I need 10 number of free frames. If I have 10 number of free frames, I can load the job, even if 10 number of free frames are not available in contiguous memory locations. Okay. So using this, I can avoid the problem of compaction, which we have seen in case of MBT techniques. Okay. Now, and coming to the fragmentation, you find that in this case, most of the cases there will be an internal fragmentation, because if the logical address space is not integer multiple of the page size, in that case last page will always be less than the page size. If the logical address space is integer multiple of the page size, there will not be any internal fragmentation. Okay, but if it is not an integer multiple of page size, in that case there will always be an internal fragmentation, and the size of internal fragmentation is limited by the page size. The maximum amount of internal fragmentation that I can have is P minus 1. Okay, that minus 1 is always there, because if that 1 was not there, I won't have any internal fragmentation. Okay, so the maximum amount of internal fragmentation that I can encounter in this page memory management is P minus 1, where P is the page size, right? But you find that even in case of this page memory management, when we divide a logical address space into number of pages, we do not consider the modularity of the program. Because you always know that whenever you write a program, you are always encouraged to write modular programs, because in that case the program debugging, program maintenance becomes very easy. But it is not necessary that if you write a modular program, the program will always be efficient. It may be inefficient. But you go for modular programming because of maintenance and ease of debugging. But the moment I break an user logical space into a pages like this, I don't consider what is the logical structure or modular structure of the program. It may so happen of the same structure, a part will go to one page, the next part will go to another page. And that creates severe problem. And you will realize this problem when we discuss about virtual memory management system. Okay, virtual memory management is nothing but an extension of paged memory management. In this case, we are assuming that if I need 10 pages, the 10 pages should be available. In virtual memory management, we will see that I don't even need 10 pages to be available at a time. Even if one page is available, I can start executing my job. Okay, but that will come to later. But right now what we are discussing is, whenever I break the logical address space into a number of pages like this, I break the modular structure of the program. So even if there is a for loop, it may so happen that a part of for loop will go to page number 0, the middle part of the for loop may be in page number 1, the last part of the for loop may be in page number 2. Okay. In paged memory management, that does not lead to any problem. Even if the for loop is broken into number of pages, that will also be executed without any trouble. But in virtual memory management, this will lead to a lot of trouble. Okay. So another concept that can be used is that when we break the logical address space into a number of pages, instead of calling it number of pages, let us call it a number of partitions. I want to break the logical address space into number of partitions, where every partition will correspond to every module of the program, which is not guaranteed in case of paging technique. Okay, and these partitions will now be called as segments. So instead of paged memory management, we go for what is called segmented memory management. Okay, but the major difficulty in case of segmented memory management is how to number the segments, because some unique numbering is necessary. As you have seen that in case of paging, the page numbers comes logically from the way you break the logical address space into pages. You have page number 0, which is unique, page number 1, which is unique, page number 2, that is unique, page number 3, that is also unique. But when you go for segmentation, suppose a program consists of a number of modules. Okay. Obviously, whenever we write a program, one of the module will be a function which we call as a main function. There is a function called main. I can write a function for finding out the square root of some values. Okay. I can write some function which will perform, say, you give me tell me any name. Say factorial, yeah. So I can write many such functions, and all these functions will make a complete program. When I break the logical address space into a number of partitions, I want to ensure that this main function will go to one segment, square root function will go to another segment, factorial function will go to another segment, so that the logical structuring or the modular structuring of the program is also maintained in my partitions. Okay. Now, while doing that, what is essential is each of these segments should have some unique numbering. But how to decide that what number should be given to this segment main, which number should be given to this segment square root, which number should be given to this segment factorial, and all that. Okay, the addressing mechanism will also be different now. In the earlier case, we had page number and offset within the page. Now the addressing mechanism will be the segment number and offset within the segment. So if we can decide that what is the number of a particular segment, then the address can be segment number, which is that integer number, and the offset, that is the logical address within that segment. Using this, I can make use of similar concept to give you the physical address within the main memory. Okay, so we'll talk about details of this in our next lecture.